Set theory is just the rules of sets. Sets are just spaces or groups of things. And we have this lecture because probability theory relies on the language of set theory. So if you're not familiar with what that means, or you don't know these terms, this lecture will help bring you up to speed. If you're familiar with them, this will be review. This is just a few important definitions about how we combine groups of items. So first of all, what's a set? Okay, it's just a collection of things, usually a collection of numbers, right? Some type of number. It could be complex numbers, real numbers, integers, fractions. So a set can be open or closed. So traditionally, if it's closed, we would give it a bracket, and closed means it includes its endpoint. We want to relate set theory to probability theory, of course, right? So if you remember the probability triple, we can see immediately that the universal set in set theory, right, in the context of a random variable, that's the sample space, right? So it's the set of all sets, right? It's everything it's all the possible outcomes of the random variable, right? We want to then think of the event space as a partition into that sample space. So we're just going to learn a few terms, and then we're going to derive a few formulas, and those are going to be really important for the rest of the course, right? So we go back to our example. Remember, we throw a single die. Now that we have a nice visual way to think about our sets, we're going to talk about how they interact, right? So first example up is going to be the union of our two sets, right? In this case, the evens and the set of the values that are below 4, right? So the union of the evens and the values below 4, well, obviously that is every value on the die except for 5, because only 5 is both odd and not below 4, right? So we can see mathematically that the way that we define that is the probability of being in the union of these sets is the same as the probability of the first set plus the probability of the second set minus the overlapping portion, right, the intersection. This is a segue to our next example, right, which is the intersection between the values that are below 4 and the evens. Of course, the intersection is only the single value, right? So the only number that is both below 4 and even is 2. And you can see here that we're going to write it in terms of a conditional, right? So what we're going to say is the intersection between even and less than 4 is the same as the conditional, the probability of being even, given that you're less than 4, right? So if you're less than 4, what's the chance that you're even? Well, it's only 1/3, because there's only 3 numbers less than 4, 1, 2, and 3, and only one of them is even, times the probability of being less than 4. So that's 1/2. So 1/2 times 1/3 is 1/6, and of course that is also, we can see visually the combination between those two sets, right? Define that on a conditional, right? So now we get to a really important rule, which is called the law of total probability. And because unions and the intersections aren't usually as easy to calculate, we formulate the law of total probability in terms of a conditional, right? So it's going to be that the probability of any event is the sum across all the possibilities times the conditional of that possibility. We describe the law of total probability in terms of a conditional, but it's important to remember that when we build the conditional out of the intersection of two events, that the order doesn't matter, right? So if we're talking about A intersect B, and we say, well, let's say that A intersect B is actually the probability of A given B times the probability of B. That's true. It's also the probability of B given A times the probability of A, right? So you can see the first two examples here are just showing that you can write it either order. So of course we can set them equal to each other. And in this case, that means the probability of odd given less than 4 times the probability of less than 4 is equal to the probability of less than 4 given odd times the probability of odd, right? Simple. Seems trivial, but the big step here is now we say, okay, we're going to divide the right side by the marginal, right? The marginal being the probability of less than 4, right? So now we have a really important framing, right? So we can say the probability of odd given less than 4 is equal to the probability of less than 4 given odd times the probability of odd, the whole thing is then divided by the probability of less than 4. Right? This formula is really important. One reason it's important is because we use the proportionality here between what we're going to call the posterior and the conditional, or the likelihood, and the marginal or the prior, in something called Bayesian inference, right? So what that is it's this task where you have this set of observations, right? And so the observations are, some likelihood on some parameter space, and from there you're going to try to make an inference on what you think the parameters are of your random variable, and that's the left, right? That's the posterior, right? And sometimes that's really hard to do because the random variable that describes the conditional doesn't have to be the same as the random variable describing the posterior. So the nice thing that we can do is we can set a random variable to actually describe the space of the marginal. So here it's not a value, but it's actually a distribution. And if we choose the right one, which we call the conjugate prior, this allows us to get a nice closed form solution for the posterior. You may have also heard people saying, I have priors about things, which I think has nothing to do with statistics, but it's like a way for people to say that their biases sound smart, right? So you often hear that, and you should know, like, prior can be a euphemism for bias, but we're going to try to be responsible and use it as statisticians. So we're going to call it the marginal unless we are doing Bayesian inference, and then we'll call it the prior or the conjugate prior. But for now, we are going to work with this formula, right? This is really important. This posterior, conditional, marginal, and the marginal factor, right? What we divide the right side by. We're going to see how that equation is actually really, really useful. Before we go on, we're going to talk about what we learned about set theory, right? So real quick, it's just a description of the operations on sets, or what we actually call spaces, right? So we talked about the union, we talked about the intersection, and most importantly, the conditional, which is part of our two take-home formulas, right? So the formulas are the law of total probability, right, which is P of A equals the sum over P of A given X times P of X, right, for all X that are possible in the sample space. And then Bayes formula, right, which is P of A given B equals P of B given A times P of A divided by P of B. And of course, we know where that came from, because if we multiply the P of B back onto the other side, we know that there's a relationship between the two conditionals. So Bayes formula is frequently invoked during the context of a medical test, right? And given the fact that this is a virtual lecture because of a pandemic, it obviously makes a lot of sense to talk about testing during a pandemic, right? So first, we're just going to say, let's imagine that there's a viral test that tells you if you're positive or negative to a virus, and it has a 98% accuracy. So it's regardless of status, right? So you could have a more complex example where the test makes more false positives than false negatives. In this example, it's going to make it simple, right? We're just going to say it's 98% right, no matter if you're sick or healthy. It gives you the right answer 98% of the time, right? And we're going to have two different environments. So the first environment is going to be an environment where people aren't very sick, right? So 2% of the population is positive. I mean, that might be a lot in public health terms, right? But not compared to our other example, which is 40% prevalence, right? So very, very different, right? So it's 20 times as much. So we're going to say, okay, in these two environments, does a positive test have the same meaning? We're going to have a population of 2,500 people, so it's 50 by 50 box, and we're going to imagine first that we have a prevalence of 2%, right? So 2% is just 50. If we do that, right, we just select one row to be the inaccurate row and one column to be the infected column. If you do that, you can see that you have 2,402 negative tests and 98 positive tests. What you can see in this on the left is you can see, okay, that on the top row is the failed tests, and because there's so many more people that are healthy than sick, the majority of the failed tests are in the healthy people, right? So the entire top row is the errors, and all but one of them is a false positive. And of course, you have one person who is being told that they're negative even though they're positive. You could say that this test is a responsible test, maybe because it doesn't give a lot of people the belief that they're negative when they're actually positive. So maybe that's a good thing, right? So in fact, even though it's only 98% accurate, because so many more people are healthy than sick in this population, if you get a negative test, the probability that it's correct is 99.9%, right? So it's almost perfect on assigning people as not sick. However, we can see here that it only has a 50% rate when we talk about assigning people positive. So half of the positive tests are false positive. That's not good, right? So you can see, and it's because it's 98% accurate, but most people are healthy. So most of the errors, in fact, the vast majority of errors, right, 49 out of 50 of the errors are false positives. So here we can sum it up and we can do the math, right? So we can follow along using Bayes' formula, right? So we can say the probability of being infected given a positive test is the probability of a positive test given that you're infected times the probability that you're infected divided by the probability that you're a positive test. And we calculate the probability of a positive test by summing over all possibilities, right? So we use the law of total probability in the denominator here. And when you add that up, you see that your false positive rate is 1/2, right? Which means that if you have a positive test, there's a 50% chance you're actually infected. So we evaluated the test in a low prevalence environment. Now we're going to say, okay, imagine that same test in a high prevalence environment, right? So we can say here, imagine 40% of the people are infected. We can do the same thing, right? So we can still, because we're doing this, in a uniform manner, we can just take that top row. That's going to be all your errors, and you do all the same math. But now, right, your prior probability, your marginal for being infected is much higher. It's 40%. If we do this, we get 97% accuracy for positive test, right? So if you test positive, there's a 97% chance you're infected. So you can see that's probably better, right? You can see that if you have a very high prevalence of a virus in your environment, then 98% accuracy gives you pretty close to 98% of positive tests indicating true infection, right? Which is important because the percentage of people infected is something that the government and the public health service and the statisticians really want to try to figure out to sort of judge the depth of the pandemic. Unfortunately, political will or public health or real life, we don't always see the same relationship that we'd want to see between prevalence and testing. That's because, in this figure you can see that there's this big spike in New York City in, I think mid-April, and there's a spike in positive tests, in hospitalizations, in deaths, right, of this virus, and testing is low because the resources to test aren't there. So of course, when it's highly prevalent, there's a move to get more tests, which is very reasonable, but of course that takes time. And as the resources are mobilized to test more, the virus drops. So by June, we hit this milestone in New York City, right, of over 2,500 tests being performed a day. Unfortunately, June, the prevalence has dropped, vastly since April. So we're now, testing, new highs of people, but the prevalence is much lower. And we're not adapting to that, of course, because we make a promise that in August we're going to be testing 50,000 people a day, doubling it, which, as we now know, by looking at this, we can see that as prevalence drops, spending more money to test more people will actually give us more false positives, which might not be the goal, but, there's some argument that maybe more tests are better. Okay, so enough about pandemics. Quick review, what we talked about today. Well, we learned about the relationship between the union and the intersection, right? So we're going to formalize that now, and we're going to call that the inclusion-exclusion principle, right? So we talked about it in the case of 2 events. It works for 3 events too, right? So if we want to talk about the union of 3 events, that's going to be the event that is the first event plus the second event plus the third event minus all the pairwise intersections. But then you have to add back on the part that you unjustly took away, so then plus the intersection of all 3, right? So it doesn't matter how many you have, you always follow that pattern to relate the union and the intersection. We also talked about the law of total probability, right? So that allows us to represent the probability of any event as the conditional times the marginal and sum across that as long as we're summing over the space of all the marginals, right? And finally, we talked about Bayes' formula, right? So Bayes' formula relates, two conditionals to each other. We talked about how that helps us understand the relationship between two conditionals. In our example, our conditionals were the probability of testing positive given that you're sick, and the probability that you're sick, conditioned on or given that you have a positive test. We talk about how those are related and the relationship of those and how they change depending on how the marginal probability of being sick changes, right? So that should do it for this lecture. So I'll see you guys next time for more random variables.